Okay, so we're going to look at classifying triangles in 3-space. So we've kind of written what we've got here. Here's our representation of 3-space. These are our 3 major coordinates. Okay, so we have coordinate 1, coordinate 2, and coordinate 3. We plotted them and kind of connected them to build our triangle in 3-space. And we have a couple rules here. We have our dot product rule, okay, which the dot product of 2 vectors is equal to the magnitude of one vector multiplied by the magnitude of the other vector multiplied by the angle between those 2 vectors, or the cos of that angle. And if we're finding the magnitude of a vector, we use this formula, the root of each of the coordinates in 3-space. Thank you. So the first thing we're going to do is we're actually going to figure out what the angles of each corner or each vertex of this triangle are. So we're going to use the dot product to do that. So we're going to choose sides as we go through. And as we choose sides to go through, we're going to have to classify each of these vectors. So like we're saying, we have our points, but we're going to need our vector projections. So we need the vectors between 2 points, which we're going to need actually this formula with also. So we're going to actually have to find the projection vectors for both of these. So we'll maybe classify between point 1 and 3 as our first vector. We'll call it vector A. And from point 1 to point 2, we'll call that maybe vector B. So these coordinates are going to become important for us. So for vector A, just to start, vector A is going to deal with 2 points. So we'll call A1, and that'll be coordinate 1, is 5, 0, 0. Okay, so that's our first point, 5, 0, 0. And A2, which is our, actually, sorry, for vector A, it's 3, right? We're looking at point 3 for that one. So A3 is 0, 0, 5. 0, 5. Okay, we essentially have to put it through this formula here to find our vector A. So vector A, this being our x, our y, and our z, 0 minus 5 is going to give us our negative 5. Okay, 0 minus 0 is 0, and 5 minus 0 is 5. Okay, so here's our vector A. We've just figured that one out. So we'll give that a value, negative 5, 0, 5. Okay, vector B deals with, we'll call it B1, which is essentially coordinate 1. Again, is our 5, 0, 0. And B2, which is coordinate 2, which in this case is 0, 5, 0. Okay, we put it through the exact same formula to find vector B, and that will give us 0 minus 5. Again, the same idea, negative 5, 5, 0. And finally, we might as well find our C vector here, which will be between points 2 and point 3. We'll call it C2 and C3. C2 is 0, 5, 0. Does this make sense? Mm-hmm. Okay, and 0, 0, 5. Same formula for vector C. We get 0, negative 5, and 5. Okay, negative 5, 5. So we'll kind of write these in. This was our B. We said was, I better write it in, negative 5, 5, 0. So negative 5, 5, 0. And finally, this will be our vector C here. Vector C we said was 0, negative 5, 5. 0, negative 5, and 5. Okay, so we've now found our 3 vectors, which is great. So now that we've got those, we can find out the angles between specific vectors. So let's find out our angles between vectors A and B in this case. So these are going to be really important for here. Maybe even zooming out a bit might be a little beneficial. Actually, what we'll do is we're going to jump to a whole new page. So we have our 3 vectors. First thing we want to do is find the angle between vectors A, B. So we're going to put it through our dot product formula here. Now, in order to do that, we're actually going to have to find the magnitude of our 2 vectors A and B. And the magnitude of those vectors, we wrote on the other page. But essentially for the magnitude of A, and this will become really handy, so this is information we're going to use throughout the rest of it, is we're going to be looking at the square root of negative 5 squared. Okay, negative 5 squared plus 0 squared plus 5 squared. Okay, which is really going to give us 2 25s, right? And the 2 25s together is going to give us the root of 50. Does that make sense to you? Okay, great. While we're at it, we might as well just find the magnitudes of the other ones because those values are going to be important to us. So we'll quickly find the magnitude of vector B. And just by looking at these numbers, you're essentially going to get the same thing because we're looking at the negative 5 squared and 5 squared will give us 25 again. Together will be 50. So our magnitudes are going to be identical in all of these. Does this make sense? Okay, so already we can probably deduce what type of triangle we're going to have. What type of triangle is this?
An equilateral triangle?
Yeah, it's going to be an equilateral triangle, but they might want more proof than this. And technically, if all our sides are the same length, then by default, we have to be an equilateral triangle. But let's say they want more proof, and we want to use our dot product to find our angles. We have our magnitudes. We're going to use our dot product and our magnitudes to isolate for cos theta. So I'm going to rearrange this formula. Cos theta is actually equal to A dot B divided by the magnitude of A times the magnitude of B. Okay, and I'm gonna. Okay, so our A dot B is essentially going to be the multiplications of vector A and vector B. So let's kind of do that on the side here. Our cos theta, I'm going to kind of speak out loud here. We're going to be taking negative 5 times negative 5, which is going to give us 25. Okay, plus 0 times 5, which is going to give us 0, and 5 times 0, which again is going to give us 0. So we have 25 over, and on the bottom, well, we already found the magnitudes of these are root 50 times root 50. So we're going to be left with 25 over, and what are the two root 50s together?
50.
Yeah, 50, which gives us a half, okay? And cos theta, we're just going to find the inverse of our half of 1/2 of cos. Let's get our calculator out here. Are we in degrees? I'm not sure if we are in degrees. But 0.5, actually I think I can do second function, cos 0.5. I think I'm in radians here. Okay, my calculator is in radians. So this one will be in degrees here. We're looking at 0.5, second function cos, 0.5999, it's 60, okay? And we know from our equilateral triangles that our angles all need to be 60. Technically, to be true, we should prove that 2 of them are 60. So we'll prove one more set, but we already know. But we might as well. So let's find cos theta. Let's go this time between vectors B and C, okay? So we'll do it in blue. Cos theta, same idea of vector B dot vector C. We already know the magnitudes, all right? They're both root 50. So we know that our denominator is going to be over 50. So as long as we're 25 on top, we should be fine. So according to this, negative 5 times 0, well, that gives me 0 squared. Okay, so 0, or not squared, sorry, it just gives me 0. 0 plus 5 times negative 5 is negative 25. So minus 25. And 0 and 5 is 0 again. 0. So in this one, we're going to get negative a half above everything. And our negative a half, let me make sure here, if we have, we're finding theta, 0.5 when it's negative, second function cos, we get opening of 120. Okay, so I ran into an issue because I got negative a half, which gives me 120, which can't be the case with an equilateral triangle. So I went back to our first page, and we just have to draw on the idea of which direction the vectors are going. And it's actually really important in 3-space. For my vectors A and B, my vector projections were outward this way, so that I could find this angle between them. Okay, so when I did that, I took 3, subtracted 1. I took 0.2, subtracted 1. And that's how we got, we took 3, subtracted 1, 0.2, subtracted 1. Worked out great. The other vector we just tried to find was between C and B, we said. Well, this projection vector, our C, I took 3, subtracted 2. 3 subtracted 2, I got this. But in my B, I was using a vector going this direction and another vector going this direction. We both want them going out from that point. So I had the opposite direction vector. So what I needed to do is I need to actually take 0.1 and subtract 0.2. And if you look, I fixed it here in purple. If I take 0.1 and subtract 0.2, okay, so 5 subtract 0 gives us 5, 0 subtract 5 gives us negative 5, and 0 subtract 0 gives us 0. This vector now is from our point C. They're both going out from that coordinate. Okay, so we can find this angle. So we go back to the other page. This is our new vector. Okay, so this gives us a different vector because it's a different direction. So when we go to find the dot product between vectors C and B, 5 times 0 is 0. Negative 5 times negative 5 is positive 25.
Mm-hmm.
Okay, so it gives us a positive, and maybe I'll just erase the negative that was there. I think that'll go in a sec. Yeah, okay. And then finally, our last point is 0 times 5 is 0. So this gives us positive 5. So this was a mistake. This was wrong. It should be 1/2. And we know that the cos inverse of a half or angle is going to be 60. And if we know if 2 of the angles 60, then 3 of them must be 60. And therefore, we can safely say that this is an equilateral triangle from all this information.